Welcome back, guys! In the previous episode, we've been looking at variable selection heuristics, and in particular, we've looked at min-dom and degree-based heuristic, as well as blends culminating with wdug. Today, we're looking at another one, a famous one known as impact-based search. So without further ado, let's get going. So the idea behind impact-based search is to try to take a branching decision based on the impact it will have on the rest of the search, on the future search. And the question is like, how do you figure out, what is an impact? What is that going to be? Well, I already made the point earlier that your choice of variable will have an impact on the size of the search tree underneath. And it's of course very difficult to have an oracle to predict how big the search tree underneath is going to be. But we could estimate the size of the search space that underlies that. So if you have a CSP like here, that is a triplet, variable domain constraints, you could estimate the size of the search tree by the cross product of the size of the domain. So take the domain of every variable, its size, multiply them together. That's an estimate of how big the search space is going to be, right? And this is neat because now we can say, if we pick a variable and we branch on it, by propagation, that search tree is going to shrink. That search space is going to shrink because via propagation, when you fix a variable, other variable will lose values. And as they lose values, the size of that search space shrink. So as we make decision, the size of the search space shrink, and the amount of shrinkage is a direct function of the variable we pick. Now, you could think of the problem as follows. As we trace a path going down the tree, we're going to create a sequence of problem, like P0, P1, P2. At some point, we'll have a Pk minus 1. That's the node we were on. And we're considering adding a new constraint that is a branching constraint, a decision which fixes variable x to value a. As a result of doing that, we're going to get another CSP, the next one down the line, which is xk, dk, ck, where ck is the same one as the beginning plus the extra constraint, right? The one we've added. And we've accumulated all the branching constraint along this path. Now, if you do that, you can, of course, use the estimator we just talked about on the previous slide. Remember, this estimator SP, which is the product of the domain sizes, we can use it and compute a ratio. The size of the search space before the decision and the size of the search space after. If you take the ratio, this is going to give us a number. So what is this number going to look like? Well, if you think about it, if you make a decision that has no impact, and it's possible, right? You fix a variable to the value it already has in the CSP. It will have no impact. In that case, the size after and the size before are equal because there will be no propagation. So the ratio would be 1. So the ratio is 1 when there is no impact whatsoever. Now imagine the opposite. You pick a variable and a value and you make that branching decision, and as a result, there is so much shrinkage that the entire search space collapses because the problem becomes infeasible, right? So 0 tuples left. That's the smallest search space you can have. In that case, it's going to be 0 over the previous size. The ratio is 0. So clearly, this ratio is going to be between 0 and 1. 0 when you're experiencing a full contraction, and 1 when you're seeing none. Now, what we can do is take the complement of that, 1 minus the ratio, and we therefore get this formula. The 1 minus the ratio at 0 will mean no contraction, and at 1 it will mean we had a failure, and therefore we had full contraction. The search space vanished, right? The ratio was 0, 1 minus 0 is 1, we had a failure. So that's what we're going to call the impact of the assignment x equal a at depth k for that specific problem, right? So impact between 0 and 1. 0, no contraction, 1, full contraction. Right? So that's the basic idea. Now, based on that, what can we do? Well, we can always, at a point let's say k during the search, look at potential assignment like x equal a, x equal b, x equal c, or even x equal a, y equal a, z equal a, and consider different variables and look at their impact. And we would recommend to do what? To, of course, branch on a variable that leaves you with the smallest possible tree after the fact. That's the basic idea. So, how are we going to do this? Well, reality is that if we had a posteriori the entire tree, we could compute an average over all the nodes in the search tree of the impact for a specific decision. And that's what this formula is giving us. I bar is going to be the impact across the entire set of k nodes of the search tree. It's going to be the average, so it's 1 over the size of k, of the sum of the impact that you have for the decision x equal a. So you see x equal a across the tree, across that set of nodes, how much of an impact it has. It's an estimate, and it's basically assuming you have the entire tree. Well, we don't, right? And we don't have the tree, so we need to approximate that. And instead of having this beautiful closed form formula, we're instead going to use an update rule that basically considers that the estimate of the impact of the assignment of x equal a is an average of two things. It's a weighted average. It's the impact that we had with one less node, right? It's the previous impact multiplied by 1 minus alpha plus alpha times the impact now at the current node we are. And depending on the value you pick for alpha, you're getting a moving average, right? If alpha is between 0 and 1, imagine that if it's 0, then it's I k minus 1x a, and this part is 0 times, so this drops. So this is the only term that matters, which means that the impact is what it was in the past. If you do the opposite, and you fix alpha to 1, this term disappears, and you're just left with that. So that is the estimate of the impact, is the impact just at the prior decision. Okay, but that's the two extremes. So by picking an alpha in between, you can have some amount of memory, let it decay by having an alpha that progressively makes this term less important, and incorporate the new value. Right? So that's this idea of an exponential moving average depending on the alpha you pick, which typically would be something like 0.9, 0.95, something along those lines. Great. So that gives me an impact for an assignment. Now that we have this, we can actually put it all together. And for that, let me first remind you of this formula, right? The impact of an assignment is 1 minus the ratio of the size of the search space after divided by the size of the search space before. Now we're going to make use of that formula in the following way. I'm going to say that the size, if I want to figure out what is the size of the search space, it's going to be what? It's going to be the size of my search space is the size of the search space now multiplied by 1 minus the impact. That is, we took the formula and we isolated the size of the search space now to try and see what will be the next one. And this is kind of a neat because it's a projection of what we're going to see as a search space, as the size of the search space as a result of making the decision x equal a. Now, if that's the case, I can still see for every value in the domain what is the impact of the variable. I basically say we're going to sum up over all the value in the domain of this formula, the size now multiplied by 1 minus the impact. Now notice that the size now is the same for all the sum, so I can pull it out of the formula, right? Because it's just a constant, it doesn't change anything, and it leaves us with this final formula, that the impact of the variable is the sum across the values in the domain of 1 minus the impact of the assignment if I were to assign x to variable a. That's neat because now it gives rise to two heuristics. I get two for the price of one. First, I get my variable selection heuristic ix, and then I get a value selection heuristic that can give me an insight as to which value might be preferable, and this is I bar x equal a. Now, why is that? Notice that, again, this formula tells us that I bar is going to be 0 if we have no contraction. If we have no contraction, then the size of the search space after will be the size of the search space now times 1, right? So no contraction. And you basically see that if you have plenty of contraction, this would go towards 1. And if it becomes 1, 1 minus 1 is 0, the size of the search space after is now times something that's close to 0. It's going to be tiny. So what do we want to do? We clearly want to select a variable that minimizes the impact of the variable. That's what we want, right? And the same thing for the value heuristic. You want to pick a value that minimizes I bar for that specific assignment. That's the trick for actually doing impact-based search. This is neat. Of course, it requires a little bit of instrumentation, as you might imagine, and that's a great exercise to do, because you need to keep track of that little statistic that tells us how the search space shrinks as you make decision, right? That's the important part to actually capture that impact. But with that, I'll wrap up. That's one of the more semantic level black box searches that really looks at the effect of the constraint network on the domain of the variables and how much shrinkage you experience when you make a branching decision. So it's more semantics. It's not about the structure of the network. It's the effect it has when it propagates based on the propagators you have. This is not the only heuristic that's like that, that's using semantic information. There is another one, but that, of course, is for the next video. See you next time. Bye-bye.